Hi, my name is Sam Hum, and I'm a junior from Colorado College. This summer I worked on the CAT Vehicle REU. Our group's project was a simple, domain-specific modeling language. This is basically just a coding language tailored for the kids. Our language, DSML for Kids, will be deployable not just on the CAT vehicle, but also on the Lego EV3 robot and simulation. We wanted our coding language to not only teach kids about coding, but also be verifiably safe. Now I want to talk a little bit about our coding language.
DSML for Kids is a simple drag-and-drop visual coding language, so the user can drag blocks that they want to put into their path into the path window and connect them by dragging a line from one block to another. This is the meta model we use for our language. It may seem a little confusing with all the arrows, but it just determines the rules for DSML for Kids. One feature of our language are primitive motion blocks. They control the vehicles to move. There are 5 possible movements: straight, left, right, zigzag left, and zigzag right. Another feature of our language are primitive control blocks. They include conditional blocks and looping blocks. The conditional blocks are the if statement and the while loop. They have 3 conditions: safe left, safe straight, and safe right. These conditions utilize the 6 scanner on the CAT vehicle and the ultrasonic sensor on the Lego EV3 robots. The user can double-click on the conditional blocks and drag motions into them. Then by taking a scan of the environment, if the desired direction is safe, then the code within the block will execute. Loop blocks include the while and the for blocks. The user can also double-click on these loop blocks and drag motions into them. The while loop checks sensors, and if true, executes the code until the direction is not safe. For blocks, on the other hand, do not check a direction. They just execute a specified number of times. This is set by the times attribute. The last features we wanted to include were turn signals and the horn on the car, but we ran out of time to implement them, so maybe next year, students can work on that. Next, I want to show an example path on the Lego EV3 robot and the CAT vehicle. In this example, the vehicles turn right, then go straight, and lastly, if safe, they turn left. On Lego with no obstacle, on Lego with obstacle, and lastly on the CAT vehicle shown on 2 times speed. Next, I want to talk a little bit about our verification. We wanted DSML for Kids to not only teach kids about coding, but also be verifiably safe. To do this, we actually implemented multiple layers of verification, using both custom verification and off-the-shelf verification tools. This may seem like overkill, but when we're working with kids and technology that probably costs more than my tuition, it's better to be safe. Our verifications run at design time, compile time, and runtime. Our custom design time verification occurs whenever a block is dragged into the window and it updates the car's current location. We start at the point 0, 0 at the bottom left corner of the grid, facing north. If we drag in a straight block and look at the terminal, we are 1 grid location north from our previous position. And now if we try to take a left outside of the grid, the terminal notifies the user that the move is unsafe. The terminal notifies the user if the car goes outside of the grid or if the car is at the location of an obstacle. Our custom compile time verification occurs when a path is finished being built and if the car is not in the proper position or not facing the proper direction that the user specified. Lastly, the custom runtime verification happens whenever the car gets too close to any obstacle within a minimum safety threshold. For example, if your teammate's in front of the car will stop once it gets too close, and once your teammate moves out of the way, the car will resume its path again. We also implemented an off-the-shelf verification tool, DReach. It does similar verification to our custom design time verification and runs on a separate server. DReach does reachability analysis, and this basically means it explores all possible paths that the car can take from its given position and ensures its safety. It is invoked every time a new block is added to the path. Now I want to talk a little bit about my contribution to the project. With the help of past REUs, I adapted the meta model and interpreters for the language. I also wrote controllers for not just the CAT vehicle, but also the Lego EV3 robots. Lastly, I wrote the custom verification at design time, compile time, and runtime. The only thing I didn't work on was the DReach verification server.
Now I want to say how rewarding and exciting this project has been for me. I didn't learn about coding until high school. If I can inspire at least a few kids to have the same level of coding that I have, it'll be all worth it. I'll say how grateful I am for this opportunity. And I would like to thank the University of Arizona,
especially our CAT Vehicle Coordinator Nancy, the head of the department, Dr. Bose, my group members, Alex and Riley, my mentor Matt, and finally, the NSF for funding the CAT Vehicle and HF projects. Thank you.